So law of sines we were using yesterday, whenever we had an angle in the side across from it. So we call that like angle side angle or angle side. So if you're given those scenarios, that's when you're going to be using that law of sines. Now today, we're going to use the law of cosines. And the law of cosines is used, it's our learning target, law of cosines. Law of cosines is used for side. So if you're given three sides of a triangle, we call that side. Or the sassy one, when you're given two sides of a triangle and then the included angle, the angle in between those two sides like this, that's the sassy one, that's side angle side. Now you might remember there was a scenario in geometry that was really, really bad. It did not prove triangles were congruent. And it had a funny name because if you didn't call it side angle, you got to call it ASS. And wasn't that a blast to be able to write S? In fact, I wrote S on my page first period. And in came Mr. Grabo, my boss, about a totally random question that he had. And he looked up, he was like, And I was like, yep. That's how I roll. So I do want to talk to you about that side angle or ASS scenario because it's called the ambiguous case. And it's called the ambiguous case because it does not prove triangles congruent. I'm not going to spend too much time talking about it today, but do know like if you went to YouTube and you typed in the ambiguous case of the law of sines, that you'll hear teachers teaching you how if you're given two sides and an angle that's not in between, it doesn't guarantee that we're all going to be solving for the same triangle. That's why they call it ambiguous. In fact, in honors geometry, I don't know, like Mr. Sarah used to love this. I'm not sure who you guys had, but he would teach an ambiguous case of the law of sines. You had to solve for both triangles, the obtuse triangle and the acute triangle that occurs if you have two sides and an angle. So some of you are nodding like you had to go through that torture. I'm not going to torture you but I am going to give you a rule. Okay, so let's do this. When solving for the angle, to avoid the ambiguous case, of the law of sines, now notice I'm talking about the law of sines right now because today we're learning about the law of cosines, but we're going to switch in like step 2 to the law of sines. So that's what I'm talking about, that ambiguous case of the law of sines. That's that SSA case, or when I taught geometry, I used to tell them no S in geometry class, like to help them remember, like no. Can't have ASS. It doesn't prove triangles congruent. We want to avoid the ambiguous case, meaning we want to know when we are solving and we're given an angle and two sides in that ASS order or SSA order, that we will all solve for the same triangle. That I won't solve for the acute triangle, and then Cal would solve for the obtuse triangle. We would both be right, but we're on different pages. So to be on the same page, if we're solving for an angle and we're using the law of sines, we are going to solve for the smallest angle first. Okay, so today, at any point when we're solving for an angle, if we're using the law of sines, we got to think sines smallest. And that's obnoxious because a lot of times it's not the smallest angle that they're asking for. So it like causes us more work. We solve for the smallest angle, then we all know, okay, we're all on the same page. And then after we solve for the same angle, then we can go ahead and find the angle they want. Now, if we're using the law of cosines to solve for an angle, we're going to solve for the biggest angle first. And I'll show that to you as well. But sine smallest. Okay, what in the world is the law of cosines? You ready? We're going to see if it comes back. And you guys in the chat are going to tell me here if this is causing any memories to come back or if it totally feels brand new. Okay, so here I'm going to write it down. And then you tell me if it's causing memories to come back or if it feels brand new. Here it comes. The law of cosines says Well, it kind of looks like Pythagorean theorem in the beginning. It's one side squared equals the sum of the squares of the other sides. It's like a squared equals b squared plus c squared. And then we do this minus double, minus 2 times that a, nope, this one would be 2 times that b times that c. So 2 times the product of these two sides. Times, so this is the law of cosines, so times the cosine of the angle that's across from the side that we started with. So it's a squared equals b squared plus c squared minus 2bc times the cosine of a. Or, what if we're solving for side b? Well, then it would be b squared equals a squared plus c squared. But this time we would do minus double the a times the c times the cosine. This is the law of cosine, so it's the cosine of the angle across from the side that we started with. So that would be a b. Or can you envision the third one? Same idea, right? So this time it's c squared equals a squared plus b squared. Looks like Pythagorean theorem exactly. But this time minus 2 times a times b times the cosine of the angle across from the side I started from, which is c. And I don't want you to look at it and be like, oh man, I have to memorize 3 formulas for the law of cosines. I don't want you to think of it that way. I just want you to think of the pattern, right? It's a pattern. So it's one side squared equals the sum of the squares to the other side minus 2. That 2 sometimes gets students. Minus 2 times the product of those two sides times the cosine of the angle between those two sides. Part A says, how far is the sailboat from Key West at this time? So when they realize, oh boy, we're off course, how far away is it? And I think last year you did what are called bearing problems, where you had like the ship maybe was bound due north, and then it turned bearing like 90 degrees, 100 degrees, whatever it might be. Some of you are nodding yes. So you did bearing problems. So it's similar to this. We're not going to do bearing problems if that brings back any bad memories. But we do have to draw a diagram. Now, I happen to know that Naples, Florida is a little bit west of Key West. And the sailboat was trying to sail from Naples to Key West. And that would have been 150 miles. But because of the winds, it's off course. Now, I don't want you to think that you have to draw the diagram like me. I'm kind of picturing like the northern winds pushing it, coming from the south. And so maybe it's pushing it off course like 20 degrees this way. Or you'd be like, no, Mrs. Cook, I want to put my 20 degrees down this way. You can draw your triangle different than mine, and we're going to get the same answer. That's important. I'll show you why that is. So I'm just envisioning, okay, it's actually traveling along that pink ray there, right there, and this angle right here is the 20 degrees that it's off. Now, I know that this pink ray right here, this segment right there, let's see, it was 15 miles per hour and 4 hours. So I know that this is 60 miles. How did I know that? Tell me in the chat. How did I know that was 60? They don't tell me 60 anywhere. Answers are coming through. What did they do? How did I get 60? You guys. 15 times 4. Perfect. Absolutely. So you're using your distance equals rate times time. So that is your 15 times 4 to get your 60 miles. And so at some point after, a certain 4 hours, that was 4 hours. After 4 hours, they said, oh, shoot, we're off course. And they want to know in part A, well, how far off course? So we want to know this. Now, I want to tell you, you could totally draw your triangle different. Like maybe you pictured the winds coming from a different place. But however you drew it, you would still have side, angle, side. Right? You would have a triangle. There's nothing special about the triangle. And you would have side, angle, side. And that's the key. So if you're like, oh, I never would have set it up that way, don't be freaking out. You still would have set up a triangle that has side, angle, side. So to solve for part A, let's use a darker color here. For part A, how far is the sailboat from Key West? Well, I say, oh, look, I have side, angle, side. So I'm going to use LOC, the law of cosines today. The law of cosine says my missing side, I'll just call that A squared equals the sum of the squares of the other side. So 50 squared plus 60 squared in either order, minus double the 150 times the 60 times the cosine of the angle across from that side A. So across from side A was that angle that was 20 degrees. So those of you that said you're drawing a complete blank and you can't remember, hopefully this makes sense where I put all the numbers. And out come the calculators, as they should. Nicely done. Somebody's having flashbacks of proofs. Oh, because I'm bringing back lots of geometry. Don't worry, don't worry. They have put a sad face. Proofs would make me smile, but, you know, I'm a little sick like that. All right, get A alone. Now, this is very quick. Watch. To get A alone, you're just going to square root both sides. So all at once on your calculator. Don't type it in little bits at a time. Just all at once, type in a square root of, and then do your 150 squared plus your 60 squared minus 2 times 150 times 60 times the cosine of 20. All at once, all in one line. Nicely done. Okay, in the chat, you guys, they are getting 95.84-ish miles. Is that okay? Good. I see lots of nodding heads. Awesome. Now, we're not done. In part B, it says, through what angle should the sailboat turn to correct its course? So here's the idea. The course that it's on is the pink segment, right? It's sailing along, and if it kept going, this is the course of the sailboat. But at some point, like here when it intersected A, it thought, oh, shoot, we better turn. So it would have to, instead of heading this direction, it's going to have to turn and head this direction. So this is my angle theta. Notice theta is outside of the triangle. Theta is this, however it would turn to head back towards K. It's outside of the triangle. But if I could find the angle that's right next to it, its supplement, this angle right here, if I could find that, then I'd be good to go because I can just subtract from 180. So now my attention has turned to this angle. But wait. This is the important part, and this is the funky part. I think this is crazy. I can't just dive in and solve for that angle. I can't. What I'm going to do now is move to the law of sines. So let me make a note back up at the top, one last note at the top. I'm going to use the law of cosines once, use LOC once, and then I'm going to switch to the law of sines. Then I switch to the law of sines if I need more, which we do in this case. We do that traditionally because people find solving the law of sines is easier with cross multiplying. So we're going to stick with law of cosines for the first step, and now we're solving for an angle. Let's switch to the law of sines. But if I'm solving for the angle, right now I would be using the information from a side, and an angle that's not in between. That's problematic. So we all have to figure out the same triangle. So we're going to solve for the smallest angle first of the triangle, the smallest angle of the triangle. Somebody's asking, why wouldn't the angle across from 150 be the answer? And the angle across from the 150 wouldn't be the answer because if you're thinking about like, oh gosh, I was going to try to draw a boat. I'm not going to even attempt that. But the sailboat is sailing this direction. So at some point it has to say, oh, let me turn towards the Key West. So as it turns towards Key West, that is that exterior angle right there. So you have to kind of envision what's happening. Now I cannot solve for that little dot right now because look, that little dot is across from 150. That's the biggest side. So this across from is the biggest angle. Instead, I'm going to solve for the smallest angle, which is angle K, which is across from the 60. Okay, that's the smallest angle. So I'm going to make note of that because that is often forgotten. So we have to solve for the smallest angle first. And that in my triangle, the smallest angle is angle K. My 60 is across from the K, so the sine of K equals, and I figured out my 95.84 over the sine across from that side was the 20. All right, let's talk about solving this on the calculator. I'm going to cross multiply. I'm going to cross multiply. So watch what happens. I get 60 times the sine of 20 equals the sine of k times 95.84. So I better divide both sides by the 95.84. And then this is what one of our students was talking about, 95.84. When they asked, when do we use that inverse button? This is it. And there were some on the homework like that, where you were solving for the angle. And so this is where you have to use that inverse button. So see how I'm going to try to get the k alone? I have to undo the sign. So to undo the sign, I will take the inverse sign of this side. That gets rid of that. And the inverse sign of this. I'll show you that on the calculator. It looks like this. Let me actually start it from scratch. Okay. Trig, inverse sign, because I'm solving for an angle. Control division. 60 times the sine of 20 divided by, now if I had that number, that 95.84, I really don't want to round it, so try not to round it. One of my favorite things to do is to do Control C. Like I probably would have highlighted the answer. Control C copies it. And then when I come back down here, I would have just done Control V to view it, to paste it. It's pretty sweet. Control C and Control V is a really nice way of doing that. There's multiple ways to do that. But you're going to get 12.36-ish. Somebody said they store it. They like to store it as a variable. I like that too. The stow button. That's a cool way to do that right there. Guys, after all of that, remember when somebody said, I remember these taking forever? Yes, because this isn't my answer. What? After all of that, 29.36 is not my answer. That was angle K. So now we go back and we say, all right, we can do this. So I can solve for the dot there by doing 180 minus this, but then I'd have to do 180 minus that to get that angle theta. So it always is true that this theta is going to be the same thing as my 12.36 plus that 20. So my final answer, it better turn 32.36 degrees. Part C. How much time has been added to the trip because of this? How much time? Well, we know that distance equals rate times time. So in part C, now I have all the information I need. I just need to do a little bit of division, right? So in part C, I know that distance equals rate times time. And they want to know, well, how much time have we wasted? So let's say, well, time would be distance over rate. So let's figure out, okay, what did they want to do and what did they actually do? So the intended route, what they intended to do was to go 150 miles and to be traveling 15 miles per hour. So the rate was 15 miles per hour. So if they had done that correctly, they would have been there in 10 hours. Okay, it's a 10-hour trip. The actual route, thanks to the winds, they actually went how far? Well, think about that. They went 60 miles and then they figured out, oh, shoot. So they went 60 miles. So then they had to turn and then they went another 95.84 miles. So they actually went 60 plus the 95.84 miles and they were traveling at 15 miles per hour. I'll just tell you what I got. I got 10.38 hours. So the answer is they wasted 0.38 hours. They wasted 0.38 hours. How could I really quickly figure out how many minutes that is? Because it feels weird to me to say 0.38 hours. So what can we do with that? Step maybe, just so I don't have to be weird and say, oh, 0.38 hours. Let's just do 0.38 times 60. and you get like almost 23 minutes. So not too bad. They wasted 23 minutes of their time. So I'm envisioning a baseball problem on the test. And I thought, well, you probably have to know some basic things about baseball in order to do well on it. So I tried to be more descriptive on the test. But some things that you should know is that a baseball diamond is actually a square. So it's a special diamond that's a square. Okay, so we have all of our right angles at the bases. We have a home plate, and then we circle the bases, first base, second base, third base. Okay, and then there's a pitcher's mound. So pitcher's mound, this one says the pitching rubber is located 32 feet from home plate. So that's along this line between home plate and second base. So I'm going to label that as 32.5. And what I'm hoping you remember from geometry is as soon as I did this, you guys, or if I did this, if I drew this whole big segment here, this diagonal of a square, that you would remember that the diagonals of a square bisect the angles. That's an important feature here so that we get an angle. We know that this angle here would be 45 degrees, and we know this angle here would be 45 degrees. So that's important to remember that the diagonals bisect the angles of a square. Now that we have everything we need because we know that the sides are each 50 feet. So I'm going to label this as 50 feet. And they want to know, well, how far then is this from the pitching rubber to first base? So they want to know that piece there. So I have enough information for side, angle, side. And as soon as I say, oh, side, angle, side, the sassy one, I'm thinking I got to use that law of cosines. And that's something you have to have memorized. You have to know that law of cosines. And so it's going to be one side squared equals the sum of the squares of the other two sides minus double the product of those two sides times the cosine of the angle that's across from side X, which is that 45 degrees. That's that pattern that you have to know. Now, I'm going to get the X alone by square rooting both sides. I don't do plus or minus because a negative distance doesn't make sense. But I'm in that habit whenever I square both sides, I think plus or minus. So I don't have to do that here. You type that in all at once on your calculator. And I guess because time is ticking, I'll just give you that number. You should get 35.47-ish feet. 2 decimals is fine by me. Okay, law of cosines. Not too bad. That's the learning target today. It's just a problem when you put it together with all the other questions that they ask. The next question says, how far is it from the pitching rubber to second base? Now, there are multiple ways to do this, but I'm going to give you a clever way. Like we were just looking at this like little green triangle here to do part A. I actually want to look at, I would argue that it's pretty quick if I look at this big blue triangle, so half of this square, that I could know pretty darn quickly some distances. And that has nothing to do with law of sines, nothing to do with law of cosines. It has everything to do with the fact that this is 50 and this is 50. And therefore, I know that this guy, this pink diagonal here, is 50 root 2. Did you ever remember that? It's a 45, 45, 90 right triangle. So they're in the ratio of 1, 1, and a root 2. So that's 50, and that's 50. So this piece here is 50 root 2. So there are multiple ways to do this, and you certainly could do it a different way. But I thought, I'm going to show you the quick way. The quick way is to realize, hey, it's a 45, 45, 90 right triangle in blue there. And so that has a ratio of sides of 50, 50, and then 50 root 2. Now that's the whole pink side, and they didn't want to know that. They only wanted to know, oh gosh, where's the highlighter? Here we go. They only wanted to know from second base to the pitcher's mound there. So I just have to do a little bit of subtraction. 50 root 2 minus 32.5. And I would get about 38.21 feet. Definitely more than one way to do that part. Okay, but part C, if a pitcher faces home plate, through what angle does he need to turn to face first base? It's the angles that get me. The angles are like, okay, I got to pause. I got to figure out what angle they even want. So he's facing home plate. He's going to turn to face towards first base. So they want this angle there. But the problem is I cannot just jump right into that angle. So that's why I'm trying to get you to pause when you think about angles. You can't jump right into it. You have to find the smallest angle first because we're going to use that law of sines. So for part C, I must find the smallest angle first because I'm using the law of sines. And the smallest angle is not this angle here. That's across from 50. It would be the angle that's across from the 32.5. Maybe I'll call that like a Y or something like that. We'll just call that Y. Angle Y. So I would set up my 32.5 over the sine of angle Y, this or that, equals, what did I find that to be? X was 35.47 over the sine of the 45. Since we have a couple minutes left, I want to remind you of one more thing, because you guys were seeming a little bit iffy about whether you'd seen the law of cosines or not. Some of you are like, yeah, definitely. Some of you are like, I don't really remember. So before you go, can you just flip to the back side? Let's not worry about this answer here. Let's flip to the back side. And the last minute, I just want to remind you about the side, side, side scenario. And that's just because we didn't get one like that. We only did the sassy one, side, angle, side. But if you were given a triangle, and you had the three sides, let's say that they're a 4 and a 5 and an 8 or something like that. I know it's not drawn to scale. But I just did a plain old regular triangle, nothing special about it, 4, 5, and 8. Well, I would say that this is side, side, side. So I'm going to use the law of cosines. Now, if I'm going to use the law of cosines to solve for an angle, I want to solve for the biggest angle first. So across from the biggest side is the biggest angle. So I would solve for the largest angle first. Cosines is different. And so it would look like this. It would say 8 squared, because that's across from the angle I want, equals 4 squared plus 5 squared minus 2 times the 4 times the 5 times the cosine of theta. And now you have to remember how to get that theta along. Well, see how they're just adding these things? So let's just subtract them over. 8 squared minus 4 squared minus 5 squared. That gets rid of that and that gets rid of that. And then they're multiplying by negative 2 times 4 times 5. So I would divide by the negative 2 times the 4 times the 5. So that gets rid of that, that, and that. Big last step at the end here, trying to get the theta alone. So you have to take the inverse cosine. So next week is all about practice, you guys. Next week we will be practicing